recording. So yesterday, I started talking about these things called insulators and conductors, right? The idea of an insulator is that it is able to hold charge, like that little plastic rod, okay? But charges are not free to move around in an insulator, okay? Okay, and these are, tends to be plastic, right? Let's just go down here, right? Insulators usually is, plastic is a good insulator. Wood is a good insulator. Glass, sort of. I wouldn't try to shield myself with electricity with glass, but it is a decent insulator. And the reason for that is because these type of material have covalent bonds where the electrons, these little blue circles, are supposed to represent the electrons, even though we don't really view the atoms this way anymore. Okay, they're kind of stuck between the nuclei and therefore are not free to move. So electrons not free to move. Okay, so if you have a material, let's say you rub some wool on this material, you get an extra electron here, but that electron is not free to move around, right? So that's what I talked about yesterday. But on a metal / conductor, because you can just use them kind of synonymously, okay? So basically almost all metals are conductors, okay? Instead of the so the electrons being bonded to each of the atoms, these electrons are kind of free to roam around. So this is the nucleus, right? And these are the electrons. They're kind of free to just roam around what's known as the lattice, meaning just the material itself. So if you were to take a piece of wool, rub a piece of metal, okay, the electrons, instead of being stuck on one particular atom, right, it's just actually free to roam around in the entire material. Okay, so that's what a conductor does. Okay, so if you put insulators and conductors together, something interesting kind of happens, right? For example, right, if I rub my plastic rod once again with my wool hat, okay, what happened is that the part that rubs, right, which is this part, right, that's the only part that has the charge collected, okay? The other part that I did not rub actually does not have charge, right, because those electrons are not free to move, okay? Similarly, where the wool is almost it's sort of it's halfway between a conductor and an insulator. The charges are actually kind of free to move around, okay? But you're using that entire wool to move stuff anyway, okay? What's more interesting is that if you have something that's like clearly insulator, clearly conductor, right? What happens is that, well, if you take a plastic rod that's been charged, right, and you touch a conductor with it, okay, instead of the conductor only being stuck at that little corner, those electrons are actually going to be moving around until they kind of get equally distributed on the conductor itself. Okay, these electrons are free to move, right? So the reason for that, we're going to see that, is because each of these electrons are trying to repel each other, right? So they're trying to get as far away from each other as possible, right? Okay. So that's why they kind of get equally distributed amongst the surface of the conductor. Okay. And this is known as electrostatic equilibrium. Okay. When you see electrostatic equilibrium, it just means that the charges are not moving around anymore. It doesn't mean there's no charge, right? It just means they're not moving around anymore. Equilibrium means no motion. Okay. You can also do other funny things with conductors, right? For example, if you had a charged conductor here, like metal / conductor, if I was to touch it, just like if I were to touch that metal ball, right, all the charge will actually move on to me. And now, me as a person is going to be charged. And then until I touch, a door or something that could ground it to the earth, right, that charge remains on me. Because both humans are also conductors, by the way, right? We are a pretty decent conductor, actually. So that charge is going to remain on me. And that's what I talked about yesterday, where, if you were walking on carpet, on a dry day, what happened is that you will build up static electricity on you, and that electricity actually going to be kind of equally distributed amongst yourself. And then when you touch a door, right, what happened is that all that charge exits your body very quickly, and therefore give you a little shock, right? There's another effect that we didn't get to talk about yesterday, is this effect of charge polarization. Remember when I rubbed that plastic rod and I just sprinkled some little pieces of paper on the table, right? Somehow the rod is actually able to interact with the paper, right? The paper was not charged, right? The rod was charged, right? But so this is neutral, okay? So how does that happen, right? Remember, the idea is that both things has to be charged for them to either attract or repel each other, right? So what happened is that this is an effect called polarization. So there are different materials. So for example, paper is highly polarizable, okay? What's really happening is that inside the material, let's actually, let me draw this before, so let's go back in time before this next picture, right? Okay, so if you have a piece of paper, for example, paper, right? Typically, the plus charges and the minus charges are kind of in the same places. Well, they are kind of like just equally distributed among the material. Okay, minus, minus, plus, minus. I shouldn't have drawn so many plus and minuses. Okay, okay. But when you put a plus charge thing near it, let's say using a glass rod, okay, a plus charge, right, is going to attract these little negative charge towards it while repelling the positive charge away, right? So what happened is that it actually moves the bottom minus charge closer to it, okay? And this effect basically was known as polarizing, where instead of the plus charge and minus charge kind of randomly being distributed on your piece of paper, right? More of the minus charge are now on the top surface. More of the lack of negative charge is now on the bottom surface, okay? Okay, and the reason that the paper gets attracted to it is because the force, right, that attracts between the plus and the minus, right, is bigger than the force that repels them, right? So this is the force of plus plus. This one, where's my purple? Yeah, purple ink, okay? This is force plus minus, right? Remember when they're opposite sign, they will attract, right? Right, and when there are same sign, they will repel each other. But the minus charges are closer to the plus rod, where the positive charges are further away. So there's some sort of relationship between how far the materials are and how strong that force is. And we're going to see that tomorrow with this equation that we're going to learn about called Coulomb's law, which is actually allows you to calculate exactly how big these forces are, okay? So this is in fact, essentially this piece of paper got polarized because it's near some positive charge, okay? Other things that are very easily polarized are like water. Water is highly polarizable, okay? A lot of organic materials are highly polarizable just because things are able to move around inside organic materials very easily, okay? So this creates this thing called an electric dipole. We're not going to go into kind of calculating this right now, but we're going to see this in a couple of chapters. So that's why I want to just make sure this effect is clear by the fact that by having a positive charge here, it attracts the negative charge more towards the direction of the positive charge and then repel away the positive charge, right? Because the like charges will repel, okay? And now these negative charge are closer than the positive charge, and that's why the paper actually gets attracted to it. It's not because the paper gets charged. It does not get a net charge, but it's just that the negative charge is closer to it, and therefore it actually creates a slight difference in the repulsion versus the attraction force, okay? So the attractive force is slightly bigger than the repulsive force. Okay? And that's why that interaction is actually much weaker, okay? All right, so any questions about polarization and this thing called electric dipole that we'll calculate in the future? All right, this idea that just by being closer to something, you get a slightly stronger force than if you're slightly further. Okay. Okay. All right, so now, right, the last thing we'll cover is this electric induction, okay? And we're gonna try to do this with a demonstration called an electroscope. An electroscope is actually this thing right here. It's kind of neat. Round it, right? Electroscope, it's a pretty simple device. You have some conductor up here, and that leads to two little slivers of aluminum, which is also a conductor. So it's just aluminum foil that you can find in your kitchen. Okay, you can make this at home if you want. Okay, what I'm going to do is I'm going to turn this on, make sure I don't have any of my electronic devices around. This will have a pretty high voltage here. Okay, okay. So what's happening is that this little device is called Van der Graaf generator. It's gonna make this dome up here very positively charged. Okay, it's just by rubbing this little belt. You can sort of see that this little belt is actually running around. It's pretend someone's rubbing their wool hat against a glass rod for but super fast as opposed to me. I'm gonna turn this off so we just don't have that on. So hopefully we can see this. Okay, by putting this very positively charged thing near the device without even touching it, I can actually cause the little slivers to flicker, right? You guys see that? You guys, if you can't see it, feel free to walk over, right? When I put it close to it, they kind of spread apart a little bit. You guys see that? Yeah. Okay. So why does that happen? Because I didn't create a charge on the device itself. Okay. So let's see what happens. Where's my pen? Okay. So the idea is that when you put a bunch of positive charge near it, right? If the material is a conductor, okay, let me go back up. Okay. This is the reason why the book is always, they give you the answer before they give you the previous situation. Okay. Here's my little, this is called an electroscope. Let's even put this stuff down here. Right. Normally a piece of metal, it'll just have equal plus charges, minus charges at the same spot. Right. They all kind of mix up together. But if you put a positive charge source here, like here, right, that positive charge source is going to attract all the electrons up to the top, right? So all these electrons get moved from the bottom, migrate all the way to the top, right? And that creates a negative charge on top, right? Right? But the lack of electrons, remember, there's the positive charge don't get to move, right? But it's the lack of electrons down here, right, that makes these two little slivers of aluminum foil positively charged. When you have two things that are the same charge, they're going to repel each other, right? And that's why that little electroscope moves even though I'm not even touching it. If you actually touch the electroscope, that's even a bigger effect. Okay, hopefully you guys can see that. Just ground everything. Okay. Yeah, maybe I don't even need to turn on. Okay. So if you charge up the electroscope, now I put all these positive charge onto the device itself. That's a different situation. Okay. Because if I was to touch this thing, right, let's jump over here, right? I put a bunch of positive charge now on the device, on the electroscope itself. These two little leaves of aluminum further apart. Okay. So the induction is a much smaller effect because it counts on you moving the electrons from here up to here temporarily, right? And it's a temporary effect, where if I was to touch it, it actually deposited the charge onto the device itself. And now the whole thing is positive charge. Of course, they're going to repel each other. You guys see the difference between the two? This is induction with no touching means induction. Charging means you actually touch the device and you actually move the charge from the rod all the way to the device itself. Okay. All right. So this brings up a sort of a neat example. So why is there a way for us to calculate how big this effect is? Okay. So I'm going to erase the stuff because I need the diagram on the left. Okay. So how can I relate the amount of charge, right? Let's call this the amount of charge, right? Which will be equivalent to what we're going to call an electric force, okay? So let me go back up here and draw a diagram for this, okay? So I'm going to draw this thing called a free body diagram. You guys remember that from physics 1? A free body diagram is sort of like a simplified version of a physical diagram where you're only concerned with like forces and torque, right? You only label forces and torque, okay? So the object that we're interested in is these little two leaves, right? So all I'm going to do is I'm going to draw these two leaves like this, simplify the diagram. I'm not even going to draw the diameter of that dome on top, right? We know that these are going to get some positive charge on it, right? Okay. Is there a way for me to figure out, some sort of relationship between the electric force and what other force is acting on this besides the electric force? Gravity. Perfect. Yeah. So there's electric force that's going to be pushing them away from each other, right? This is the force electric. We don't even need to know how to calculate that. Okay. The other force, right, is actually gravitational force, right? I'm just going to do the right-hand side. We can just, if we get the right-hand side right, hopefully the left-hand side will also work, right? So let's just ignore this side. Okay. So let's just think about the force of gravity, right? If you have force of gravity pulling you down, what does it do if this point is fixed? Let me demonstrate this, okay? So here's the center of mass of something. You have gravity pulling it down. What does it do? Does it fall or does it do something else? What is that called in physics 1? I'm sorry? The swing or rotate, right? When something rotates, that's a what? Torque. Perfect. Nice. You guys are remembering lots of stuff. Okay. So this force of gravity, right, is actually trying to produce a torque, and that's going to be clockwise. Remember all these subscripts, right? Where the electric force, right, is trying to push it apart. So it's actually applying a torque in the opposite direction, right? So there's going to be a torque. Just stay with red, okay? There's going to be a torque from the electric force that's going to be applying a torque in the counterclockwise direction, right? All right. So is there a way for me to relate these two forces, right? Because, right, when that electroscope is hanging up, let me get a better version of this. Pretend this is the little aluminum, right? When that piece of aluminum is hanging up here, right, there's a balance of force, balance of torque between gravity trying to pull it down and the electric torque trying to pull it up, right? So in that case, right, I know that the torque clockwise and the torque counterclockwise has to be the same, right? So how do I calculate torque from gravity? So that's what this one goes from. That's what this one. You anyone remember how to calculate torque? Yeah, Jacob? Right, force times the radius. In fact, what I'm going to do is I'm going to draw a separate diagram here, right, where you have the radius to the center of mass here, right? So the leaf is actually twice as long, right? That's the radial vector from there, right? And the force of gravity is pulling down on it this way. I'm going to declare this angle and call it theta, okay? Just some angle theta, okay? If you want to calculate the torque of something, okay, is the radius times the force times sine of the angle between the two vectors, right? So this vector here, this R vector, this theta angle is actually the same as this, okay? Well, what's the force that's pulling down on center of gravity there? Anyone know the formula for that? What's the force that's pulling down the little leaf? It's called gravitational force. What's the formula for that? Anyone remember? Yeah. Right, mass times acceleration of gravity, m times g, sine of theta, okay? So that's on the left-hand side. The stuff on the right-hand side, I'm going to draw a separate diagram, right? Once again, this is the center mass of the little leaf, right? This is the same R vector, right? Instead of pulling the leaf down, the electric force is actually trying to push them apart, right? Okay, so that has a different angle, right? That's the problem. Okay, so if I extend this out, right, this angle here is not theta, right? The angle theta is actually this one. What's the other angle that's not theta? Is there a way to figure that out? If you have a angle like this, if this is theta, what is this equal to? I'm sorry? Almost. It's 90, right? Because it's a right angle, right? It's 90 minus theta. Okay, great. So what's on the right-hand side, the torque counterclockwise, right, is R times, instead of the gravitational force, this is the electric force, times sine of 90 minus theta. Those of you who, you can look this up, right, know your trigonometry on like the back of your hand, right? You know that 90 minus theta for sine is just the same thing as a cosine, okay? If you shift an angle by 90 degrees, it'll just make it a cosine function instead. So now we know that the two sides has to be equal to each other. So the torque clockwise and the torque counterclockwise has to be the same. The left-hand side, I'm going to fill in from this R mg sine of theta, right? And then the right-hand side is just from up here, R fe cosine of theta, okay? The R actually cancel out, which is kind of neat, right? And if you solve for the electric force here, right, you get mg sine of theta divided by cosine theta. In other words, just mg tangent of theta. So you can actually, if you know the mass of that object and the angle that they separate from each other, you can actually calculate what the electric force is. Okay. Any question about that? I'm gonna switch over to discussion mode and stop recording.